Yeah, no problem.
How is everything in Netherlands?
Very good, very good. Rainy, grey, cold, but good otherwise. Not sunny and warm as in Brazil, I think.
Very good, very good. So let's start the second day of the seminar week of the Enhanced Oil Recovery Laboratory. And today we have the pleasure to have Professor Sebastian Geiger from Technical University of Delft, Netherlands. And thank you, Sebastian, for your time, for being here today. And this opportunity, I've been waiting for this opportunity since March 2020. Do you remember, Sebastian?
Yes, I know. Yeah.
Professor Sebastian was here for a short course on WAG simulation with his team, but that was exactly the same day the lockdown was established in Brazil when he had to return to UK. So it's the first opportunity we have since then to have a presentation for Sebastian, and I hope this opportunity is the first of many others in the near future, Sebastian. And again, thank you very much for your time. So we have some people here, and we have several other online in YouTube as well, as we are transmitting live. So if you want to share your screen.
Yeah,
okay.
just do this. So I've shared this. Yeah, great, excellent.
Yes, now we can see.
Okay, do you want me to start? I do hope you can still hear me, because I can don't see anyone on the camera on your side anymore. Well, thank you very much, Paulo, for the kind invitation to speak at your seminar today. It's great to be back virtually, at least at UFIJ. What I want to talk a little bit is about how we can design good models for reservoir simulation. So just get to the... So to put my presentation into context, this is the world population, the growth in world population by region from the UN projections. This week, we passed the 8 billion people threshold, and by 2050, when we all expect to have net zero targets, then we're going to be close to 10 billion people across the world. So meaning those additional 2 billion people, they all want to have access to food, to water, and to energy. And most of the growth in population is going to come in regions, Africa and Asia, where access to energy is not given on a day-to-day basis. Currently around the globe, there are about 3 billion people who do not have access to secure, affordable, sustainable energy. What those people do is you often burn very basic biofuels, wood, grass, animal dung, sometimes kerosene. So fuel sources that emit a lot of particles and a lot of unhealthy particles that affect the lungs. And what the World Health Organization estimates is that roughly that more than 4 million people die on an annual basis because of lung problems that are caused by burning inadequate fuels due to the lack of access to clean and affordable energy. And those 4 million people that die on an annual basis, those are more people combined than malaria and HIV combined. So what we do face is that energy trilemma. So we want to have energy that is affordable, that's available. We want to have energy that is green and clean, and we want to have energy that is secure and reliable. And we need to provide that energy to a rapidly growing world population. If you look at the UN sustainability goals, then this SDG number 7, access to affordable and clean energy, in my personal view, is very much at the heart of everything we do. Because once we have access to clean energy, then food becomes less of an issue. Access to water becomes less of an issue because we can sterilize water. Access to education becomes less of an issue because at the moment of these 3 billion people who don't have access to reliable energy, it's often the school children, often the young girls who have to go and collect those biofuels for burning later on. If you look where energy is going to come from, this is from the BP World Energy Outlook, and it doesn't really matter which outlook we are taking. They're all very similar in predictions. So at the moment, most of energy that we're consuming comes from those black, red, and green colors. So this is oil, natural gas, and coal, fossil fuels. And then the different energy authorities, the different companies, they have all very similar estimates for the future scenario. And there are 3 different scenarios. One is the new momentum scenario. So this means we continue to decarbonize our energy systems. And but due to the growth in world population, we're going to need more energy in the future. And we see sort of almost a stable amount of natural gas and oil that's being burned, a little bit reduction coal, significant increase in electricity and other energies, modern biofuels. The new momentum scenario, this is not going to take us anywhere close to the 2 degrees centigrade global warming that has been agreed in the Paris Agreement, in the Paris Accord. The 2 other scenarios for the future energy consumption, the so-called accelerated scenario, where we have see a reduction in global energy demand, reduction in fossil fuels, and even sharper growth in electricity from renewables, and the net zero scenario, we really curb our CO2 emissions. We make sure that we're going to reach, that we're going to stay within the 2 degree scenario. And by 2050 are net zero, and which sees a massive downshift in fossil fuels, not a complete reduction in fossil fuels. So most of the energy that we're going to see coming up in the future is probably going to be from renewables, wind and solar energy, in addition to slow decline and continuous decline in fossil fuels. And one of the problems with renewable energies is that they're intermittent. So the days when the sun doesn't shine and when the wind doesn't blow, like today in the Netherlands, so electricity is not being generated. We need to find ways to store that electricity. And how we can store electricity energy from renewables is by converting using electricity from renewable energy to generate hydrogen and then store that hydrogen as a gas in the subsurface, in depleted gas reservoirs, in depleted oil reservoirs, and pump it back to the surface in times when we need additional energy because our renewables are not working. So when I talk about designing good models for reservoir simulation, I'm really trying to look beyond just classical oil and gas applications and look for the synergies that we find between oil and gas, geothermal energy, carbon capture, storage and utilization, CCS, and hydrogen storage. So on the one hand, we have the natural gas production with as a fossil fuel, because natural gas provides us with a lot of on-demand energy. And if you combine natural gas production and the energy from natural gas with carbon capture and storage, we can get life cycle CO2 emissions, which are very, very close to renewable life cycle CO2 emissions from renewable energies. So we need to have the geological CO2 storage in depleted aquifers, depleted gas reservoirs, and we need to have this energy storage as well. So the hydrogen storage where the hydrogen was created from renewable energy sources. We use that hydrogen as a buffer for the times when literally the wind isn't blowing, the sun isn't shining. Then we can maintain a constant energy supply from renewable energy. So use hydrogen, we store it again in depleted gas reservoirs, possibly even in saline aquifers. And then geothermal energy is sort of another big factor, because in the global north, in countries like the Netherlands, UK, and Germany, but also Canada and the US, who have long, gray, cold, miserable winters, our single biggest energy consumption comes from keeping our homes and houses warm in the winter. Roughly 50% of all the energy that the global north consumes is to keep homes warm in the winter. That energy comes at the moment from natural gas, by directly burning the natural gas. And there is a lot of activity now in Europe, especially in Europe, to shift away from burning natural gas for heating homes to developing district heating networks by simply taking some low-grade heat about 50 degrees centigrade, 60 degrees centigrade from the subsurface, feeding it into district heating networks and using sustainable geothermal energy for heating and decarbonizing one of the big energy sectors. So the moment we talk about geological reservoirs, well, the subsurface, we are entering some problems. Geological heterogeneity is always a key control on fluid flow in a reservoir. It ultimately influences many engineering management decisions. So where do we drill the wells? How many wells do we drill? How many fluids can we produce, be it oil and gas or geothermal water? How effectively could we store CO2 or hydrogen in the subsurface? But geological heterogeneity is always multi-scale. It's also complex. It's not random. Geological heterogeneity is created by physical process. So it's not a random nature, it's a very complex nature. And even for the untrained geologist, if you look at the picture here on the right, you can see, so there's some geological facies here that sort of start to disappear somewhere. That would be a subsurface reservoir that start to disappear, and these black beds, they start to thin out and become thicker and thinner. So there's a lot of geological heterogeneity in the subsurface. The problem is that heterogeneity is sparsely sampled and inherently uncertain. So if we had to drill into that formation, that well is only going to sample very, very small fraction of the reservoir, and we don't know how to interpolate geological heterogeneity in between the wells. There's always going to be some degree of uncertainty. And the solution to deal with that uncertainty is that we build a reservoir model to capture that captures geology of the subsurface, and that ideally allows us to explore the degree of uncertainty, geological uncertainty, how that geological uncertainty influences fluid flow in the reservoir, be it oil and gas, be it hydrogen, be it CO2 or geothermal heat. So here's your typical reservoir modeling workflow, and this is a picture from Mark Bentley. We start with our geophysical interpretation. We do some geological modeling. We then do a petrophysical interpretation. So we assign then permeability, porosity, capillary pressure functions to the geological model. And then we have our reservoir engineering simulation. So we somehow upscale our geological model to a coarser model. For faster simulation, we do then some uncertainty assessment and forecast future reservoir behaviors. But in that reservoir modeling workflow, there's already some uncertainty. So the first one is, which data do we have in terms of geophysical interpretation? Seismic data, logs, cores. Geological modeling has inherent uncertainty. So which geological concepts are we going to, do we need to consider? Is it a deltaic system? Is it a braided river system? Is it the pre-salt carbonate, incredibly complex, different geological concepts that we could use to describe that influence how heterogeneous the reservoir model is going to be. When we do our petrophysical interpretation, the big question is which method should we use? So rock typing, taken cutoff points for permeability, porosity distribution, maybe multiple point statistics. So Gaussian models are better to distribute petrophysical properties in our reservoir given a geological concepts. Ultimately, in reservoir engineering, simulation, and the forecasting, so which physics do we need to consider? Are we single phase flow because we look at a natural gas reservoir? Do we have some very complex thermal, hydraulic, mechanical, chemical processes? If you think about enhanced oil recovery, low salinity, water flooding, natural water altering gas injection, how do we deal with three-phase relative permeabilities, with changes in wettability? So which physics are important? How do we capture them properly in our reservoir model? So all these are uncertainties that we need to be aware of in our reservoir modeling workflows. The problem we face with uncertainty is that we perceive uncertainty in a very biased way. So the first thing is we tend to be overconfident when we estimate ranges. So ranges of permeability, ranges of porosity. There's always bias in our data, and our estimates tend to lead to narrow ranges of uncertainty. So not only overconfident in how narrow a range of properties could be, permeability ranges, we also are often forget that there are bias in the data itself. A well that you may have drilled into your reservoir may preferentially sample the more permeable rocks or the less permeable rocks. So all our biases are all our data is biased towards something that's perhaps more permeable than in nature or less permeable in nature. So many reservoir models, they do not capture uncertainties properly. So if you think of if you think of uncertainty, the big picture here, the big circle is, did we get everything? So did we really think carefully through the uncertainties, the known unknowns, so that we know that permeability and porosity distributions struggle to quantify them, but also the unknown unknowns that we may have missed some faults in the reservoir, we missed some essential physics that are really important for our reservoir. Then we have the perceived uncertainty. So these are the things we can think about and we're trying to characterize and quantify. Once we define the uncertainty in a reservoir model, because of time pressures, because of lack of access to data, because of difficulties running the right experiments to get three-phase relative permeabilities for your water, alternate gas injection, how we define uncertainty in the model, that uncertainty envelope is all going to be smaller. And then once we try to estimate our uncertainty, again, because of time pressures, we can only run so many simulations, then the uncertainty estimates are always going to be less than the real uncertainties we face in the subsurface. And missing out uncertainties, key uncertainties, can have late dramatic consequence on how we think about reservoir behavior. And one is commercial impact of uncertainty. So this is from Mark Bentley's book. Here we have the ultimate recovery, excuse me, throughout the lifetime of an oil and gas or hydrocarbon reservoir, so from exploration due to appraisal, development, production, late life. So ultimate recovery in gray, when we do the exploration, we don't know how much oil and gas we're going to recover, so there's a huge range of uncertainty. And as we try to appraise the reservoir, the uncertainty envelope for the ultimate recovery starts to decrease, but it's not a continuous decrease because as we have new data, some of the thinking of the reservoir may change. So the uncertainty envelope for ultimate recovery, so slowly but surely decrease, but not in a nonlinear fashion until the very late life, until we decommission the reservoir and we know exactly how much we have produced. On the flip side, if you think about uncertainty of drilling future infill wells into our reservoir, well, this uncertainty is quite low at the exploration, appraisal, development phase because we sort of have a plan what maybe what we may want to do, but we're not drilling early in the field life infill wells. As we go later and later in the field life, then the uncertainty about drilling additional wells, infill wells, increases because we're not certain how much hydrocarbons these additional infill wells are going to produce. If you then think about the commercial impact of our uncertainties, the return on our investment, that changes dramatically throughout the reservoir or the lifetime of the reservoir. So it's quite low during the exploration. Once you appraise and make the decision to develop the reservoir, there's a huge commercial uncertainty because we don't know how much hydrocarbons we're actually going to produce. Once you're on production, the uncertainty and the commercial uncertainty start to decrease until we reach a tipping point later in the field life when any additional investment, we're going to be less and less certain how much there is going to be a return on that investment. So if we don't get the reservoir uncertainties quantified in a proper way, it has huge impact on commercial uncertainties. If you think about low carbon solutions like geothermal energy as an example here, then there are also huge societal impacts of uncertainties. Geothermal energy is produced very close to where population centers are. Pictures here are from the city of Munich in Germany, where they're planning to have 500,000 homes supplied by geothermal heat for district heating, so no longer gas boilers. So what they're doing in Germany is they're drilling wells right in Munich, right in the city center. They're running this big vibro-sized trucks through the city center to create images of the subsurface. Now, this is a huge disruption for the local population to get data that hopefully helps to reduce uncertainties. And what you see on the right-hand side are pictures again from Germany where geothermal operations caused issues, flooded streets, cracks in houses. This is not so much because of the actual geological uncertainty, but because of poorly constructed wells that didn't interact properly with the subsurface geology, and then geothermal water started to leak into formations, and you got uplift or ground subsidence, damaged streets and houses in some cases. Here's a classical example of uncertainty and bias. So this is work that was done by Claire Bond at the University of Glasgow about 15 years ago. So what they've done is they created on a computer a set of sedimentological model, a synthetic sedimentological model, and then they used another computational software to deform that stack of sediment and create some geological structures. And with a third package of software, they then created some synthetic seismic data. So they gave this synthetic seismic data set, which you see here, to a large number of different interpreters. And what was special about the synthetic seismic data set is that they knew exactly what was present in the subsurface to begin with, or because it wasn't the subsurface, because it was a model that they have created. So they knew what the right interpretation was. So the different interpreters came up with very different geological concepts because of the different experience. So some PhD students work in salt tectonics. So think about sort of things like pre-salt that are really important to understand. Saw a lot of salt features in that seismic data set. Student working on sequence stratigraphy for carbonates saw a lot of carbonate features in that seismic data set. Industry experts who worked on thrust belts, extensional basins, they saw a lot of thrust extensional features. Very different interpretations on the same data set. If you look at how the different interpreters what they came up with, the correct answer was an inversion structure, and roughly 90% didn't see that inversion structure. What I always find remarkable is about 1/3 all the interpreters were quite unclear what the actual geological structures are that they see in those subsurface data sets. So huge amount of uncertainty that is also influenced by our personal bias. And even the hard data in our model is uncertain, and again, biased because of where we tend to drill well. So this is me standing here on top of a carbonate outcrop in the south of France with Mark Bentley and some of his colleagues. And they hold a synthetic log sheet, and Mark and his colleagues, they hold the famous shower curtain that shows how much log, wireline log that we run down a well, how much it actually samples of a formation. So if we have a continuous log of a subsurface data set, then the log now shows changes in porosity, and we use that change in porosity then to model distribute permeability and saturation, etc. in our reservoir. But what we tend to forget that how porosity is being estimated in a log, that's actually already running average over sort of roughly 1 foot 30 centimeters of heterogeneity. So a lot of the small scale features, these more high permeability streaks, that tend to be already averaged out in our log data. We then start to process this data and we create a discrete log. We average a bit more, and then we build a reservoir model and we upscale the log. Then we average out the porosity even more, and we have much less geological heterogeneity in our reservoir model than what's actually in our log. And that log data is even capturing less heterogeneity than what we have present in the subsurface itself. So when we built a real reservoir model, this is a reservoir model that some of my students had built in the past, we have several kilometers in size, we have all these wonderfully colored grid blocks. What we need to remind ourselves is that each grid block is perhaps 100 by 100 by 2 meters in size. That contains roughly 5,000 tons of fluid, roughly 50,000 tons of rocks, and we assume all these properties have that volume has uniform properties. So it's a much larger volume of rock than what you at LRAP do your experiments on, for example. And somehow we take that leap of faith that all this geologic heterogeneity that we see in core, and this is some core of a carbonate rock, and you can see nicely where the pores are because they're oil stained. You have some really big pores, really complexly shaped pores, very tight rock. So, and here are some fractures in a carbonate rock. We think that we sort of make that leap of faith that some average properties, some average permeability, some average capillary pressure, average saturation reliably represents the heterogeneity we see in nature at the scale of a single grid block. So what we often face is that reservoir modeling is often slow and ineffective, inefficient exercise and compromise. It takes us a long time, months, to build the initial reservoir model. It requires us to lock in geological concepts early and really limits exploration of different model scenarios. So these concepts, are we in a structure, in what kind of structural setting? Is it a faulted setting? What I showed you in this study from Glasgow University, we really lock in one interpretation very early on, and we don't explore different geological scenarios. Our models are poor representation of a reservoir system. Why? Because all that small-scale geologic heterogeneity that we know is there from core observations, from laboratory data, we don't represent it at that level of detail in a reservoir. We tend to emphasize matching versus learning, so we try to history match production data. And once we have a good agreement with production data and the reservoir model, we're sort of happy. We don't use that history matching exercise to actually learn about what we're missing in our geological understanding, what this means for geological uncertainties, for reservoir performance forecasts, and important things like reserve estimates and so forth. So discussed, our models pretty much always underestimate uncertainty. Because we have very big computers these days, very powerful computers, we tend to create big models that are precisely wrong, not smaller models that are approximately right. At the end of the day, we often end up with two things that we don't understand, which is the reservoir and the model that we're trying to simulate itself. Again, this is a model that we have built with students in my group, and it looks very colorful, but I can't help but think that this sort of looks a little bit like someone has played around with Lego, put a little Lego well in there to approximate some geological heterogeneity in the subsurface. So what can we do better? The first rule is if you can't draw it, don't model it. So what you see here is a map view of a fluvial system and a geological sketch of the fluvial system. So if you can't draw the geological concept that's present in your reservoir, then you probably don't understand what you're trying to build. So if your model that you're building looks nothing what you drew, then your model is probably wrong. And if you have a different geological concept, so some different meandering system for your fluvial channels, different pre-salt geological concept, that also means you need to build a very different model that you just need to sketch first. Second thing you need to do, the second rule is when we build good reservoir models, we want to make sure they capture heterogeneity in the connectivity. So we want to know what is the magnitude of heterogeneity, what's the range of minimum versus maximum permeability, what's the scale of heterogeneity, so at what scale does permeability start to change significantly. What's the degree of connectivity? So here you see, again, so cross sections and map views of a fluvial system. Now, do we have fluvial channels that are really overlapping a lot and they're held laterally and horizontally very well connected, like in figure B, or are these channels much more straight lined, like we have this in this figure here, and there's much less lateral heterogeneity? Are there some clay overbank deposits that are very low permeability that reduce lateral connectivity? So we need to understand from a geological concept, do we think it's already better connected, poorer connected? We want to sketch this and test these different concepts to understand what is the complexity of the flow path. And the last thing is we need to see the geology like the fluid does. So simply put, the same geologic heterogeneity can react very, very differently depending on fluid is present in the subsurface. So assume what you see is the degree of heterogeneity in terms of permeability, and if you need to build more complex 3D model, or if you can get away with simple analytical models. So depending what's in your reservoir, dry gas versus heavy oil. Then if you have dry gas and you're trying to produce that dry gas by natural depletion, you need a lot of geological heterogeneity before the fluid really starts to respond to the heterogeneity that's present in the subsurface. So for some types of reservoirs, we can probably get away with simple analytical models. On the other hand, if you have some light oils, we inject water, you have heavy oils, we inject steam, or if we do gas injection to displace oil or water and gas injection, then we need very little geological heterogeneity, 1 to 2 orders of magnitude, before we really need to start to build a 3D model, because that geological heterogeneity, depending on the displacement process, really starts to influence how the recovery behavior. So if you follow those rules, then we can start building models that are quite reliable for reservoir performance forecasting. Again, it doesn't matter if it's a hydrocarbon reservoir or CO2 storage site, hydrogen storage site, or a geothermal reservoir. And what we then need to think is how to use these geological models to deal with uncertainty. And again, this is from Mark Bentley's, from one of Mark Bentley's paper. Basically, you can think of using models to address uncertainty and ternary diagram. Here on the top, we have our best guess. That's a base case model. So we build one model, that's our preferred base case, and we anchor every prediction around that single model. On that corner here, we have multiple stochastic models. So we take one model and then we run different multiple stochastic realizations of permeability porosity distributions for that model to look at interparameter relationships, netto growth versus permeability versus porosity, to understand geological uncertainty. And on that corner here, we have multiple deterministic scenarios. So this is where we design a number of reservoir models to explore different geological concepts. So we no longer have a single base case. Let's look very quickly at what these three different corners. So the base case, a so-called rationalist approach, where in the top corner here, you have one geological concept. So one thing, or one concept of where we think about how our fluvial channels are connected, for example, or what is happening in our pre-salt reservoir. You build exactly one model. You run that model, and you say there could be 20% more production or 20% less production, and that's how we that is how we make then the relevant engineering investment decisions. We can do maybe a little bit better and move that base case model towards a little bit towards that multiple deterministic model. We have one geological concept, and then we can build two other models, one low case, one a high case model, to look at models that represent the high, low, and base cases, and have a bit more, capturing a bit more uncertainties in estimates of future reservoir production. The multiple stochastic approach, so we're in this bottom corner in the bottom left here, we have one geological concept. We look at different parameter relations, different distributions of netto growth, permeability, porosity, to create a number of stochastically generated models for our initial geological concepts. And then we can do some probabilistic estimation of hydrocarbons in place, storage volumes for CO2, storage volumes for hydrogen, heat in place, based on which we then make forecasts of future production. The last one is this multiple deterministic approach, the scenario-based approach, where you create multiple discrete concepts, not just one concept, but multiple different geological concepts. So in this example, in different ways how the reservoir may be faulted. And then based on these different concepts, we create, on this different concepts, these different scenarios, we create then individual reservoir models. Some of them may have additional geostatistical reservoir representations. Others, maybe because the permeability distribution is relatively simple, we can do them as a much more simple analytical solutions, for example. Scenario-based approach that allows us to really explore uncertainties across a wide range of reservoir architectures is very rarely used because it's really difficult to do in practice. And this is where some of our research or latest research taps into. And what we want to do is follow that line. If you can't draw it, don't model it, to explore different geological concepts. So if you think of what geologists have done for many, many years in the past, they have drawn geological models for a long, long time. I did my undergraduate degree in geology in southern France, in southern Germany. I spent hours and hours in the Swiss Alps, in the Austrian Alps, and drawing geological sketches and admiring, which I was very poor at, admiring some of the geological sketches that these famous Swiss alpine geologists have drawn, and that colleagues of mine who could draw geology at every scale much better than I did, they have drawn. So our hypothesis is it possible to create reservoir model prototypes? So prototypes of reservoir models that explore different geological concepts interactively, rapidly, and intuitively to analyze how these different concepts influence flow at multiple scales. So do what the geologists have always done, sketch different geological scenarios, but now do this not on a piece of paper, but electronically, turn these sketches into simple geological conceptual models based on which we can do some first calculations to understand how does geological concept influence some key reservoir engineering decisions. So what we have done, and this is in work with University of Calgary and Imperial College London over the last 8 years, is to develop the so-called rapid reservoir modeling workflow, which is being released also as an open source system and a package, and you can see this link here at the bottom. So what RRM, Rapid Reservoir Modeling, does is it uses standard surface-enabled laptop or computer. We can use digital pen to sketch geological structures. In RM, we can sketch in map view and in cross-sectional view. So we can sketch geological features cross-section map view based, for example, on seismic cross-section or a geological map or some well data. And then based on some modeling engine, I'm going to talk to you, explain to you in a moment what this modeling engine is. In real time, a three-dimensional model is being generated. That three-dimensional model is always going to be geologically consistent. If we want to add more geological complexity, we don't use statistical workflows. We simply sketch more geological detail in our model, and the model then, the 3D model, updates itself. So what is different from sort of the standard reservoir modeling workflows is that we prototype geological concepts very quickly from these two-dimensional sketches that then create three-dimensional models. And with three-dimensional models, entirely surface-based, so there's no grid to begin with. We only create a grid on demand when we want to do some basic calculations. So for example, understand what's the gross pore volume in the reservoir, what are breakthrough times between inject and producer pair, and so forth. So then we create the grid, then we characterize that grid and assign some permeability porosity distributions to do some very basic, simple computations. Input data could be anything from a blank screen, outcrop pictures, geological maps, some seismic lines, can be at any scale, so small scale from outcrop all the way through to a basin scale, based on which we create these sketches, and from these sketches, the modeling engine then creates surfaces that describe geological heterogeneity. This is not to replace commercial software packages. So we still want to do, at the end of the day, this detailed geological models in Petróleo, in JewelSuite, whatever our favorite geological modeling software is, and do the full dynamic simulations, CMG and T-Navigator in Eclipse, whatever our favorite simulator is. But simply what we don't want to do in the first step is to very quickly test multiple deterministic scenarios. So what is our modeling engine? We use technology called sketch-based interface modeling, or SBIM, which has been around in the computer graphics industry for over 2 decades in companies like Walt Disney, Electronic Arts, the big car manufacturers like Fiat, technical, medical science illustrators, they all use this. The idea is very simple. So you sketch an outline in 2D. So here's the outline of a heart. And then because the human heart has a very defined shape, then a modeling engine recognizes that what you want to sketch is a human heart, then turns this 2D sketch into a 3D model of your heart. You can augment shapes. So you have hand here, and you want to add some arteries to the back of the hand. So some veins on the back of the hand. So you sketch the outline of the heart, of the veins. And then these outlines emerge with the hand to create a biologically consistent sketch of a model of your hand with some veins on the back of the hand. Or you can have this conceptual operator marking. So here's a leaf and you want to deform the leaf. So rather than rebuilding that leaf, you sketch the deformation path of the leaf and then in a biologically consistent way, because biology has its own rules. Biological structure have their own rules. That leaf is then deformed. So what we have done is we adopted this ESWIN concept to the idea of surface-based modeling, which Matt Jackson and Gary Hampson at Imperial College London have really sort of refined, and I played around with that as well in my PhD thesis. So what we do is in RM and with surface-based modeling and in the sketch-based interface modeling is that all geological heterogeneity is modeled as one or more discrete rock volumes bound by surfaces. So here, and and then we can have a hierarchy of surfaces from faults to stratigraphy, facies, diagenetic bodies. So can do anything from large scales, big para-sequences, coastal plains that are tens of kilometers in size, hundreds of meters in height, all the way down to sort of diagenetic events like burrows, small-scale cross-bedding that are tens of centimeters in size. We describe everything by a hierarchy of surfaces. As we keep zooming in, different surfaces, smaller scale surfaces describe different levels of geological heterogeneity. Our petrophysical properties, they're always constant within the geological domain. That's exactly the same as a grid-based approach, but now the petrophysical properties are constant within a geological meaningful domain rather than a grid block that has some arbitrary size. If you want more geological heterogeneity, again, you simply add more sketches rather than starting to play around with geostatistics to represent your geological heterogeneity. And to make sure that our models are geologically consistent, we have some very basic very basic rules. So imagine you have sketched these gray horizontal rules that represent some sedimentary surfaces, and we have a fluvial channel that's going to erode some of these geological surfaces, this new surface N here. And there's certain ways that the channel can interact geologically with existing surfaces. So it can either remove everything above this new channel, so it can remove that bit of the surface, this bit of the surface, or everything below that existing surface, so that gray surface, that gray surface, that gray surface, or we can say it only intersects, removes, changes surface where this new surface intersects with an existing surface. So there's some geological rules that tell us how these different surfaces that we're sketching interact. And because you need just literally around 10 different geological rules to describe, to model your geological heterogeneity in any way you want, from large scale to small scale, from old to young, from young to old, from big to small, as you interpret it. You can always redo things, undo things, gives you full flexibility to sketch what you see. How do you go from 2D to 3D? Well, we interpolate between cross sections. You may have a series of seismic cross sections. You interpret one cross section, and then the modeling engine interpolates what is happening between the individual cross section. This is a Reservoir model that was built with this RM concepts. The surfaces describe this. It's a really complex structure, lots of faults in there. That took perhaps 20 minutes to build that model, and it would be really, really difficult to test that, build that single geological concept in individual workflows. If you want to go from 2D to 3D, we could also sketch, say, a fluvial channel in cross-section. Then just in a map view, we can then sketch the extrusion of that, or the trajectory of that fluvial channel to tell the software in which direction that fluvial channel is changing horizontally. And then very quickly, we can model how these different geological channels interact, fluvial channels interact. Or we can sketch contour lines. So we can sketch again some cross sections, and we can define how these cross sections change in map view in terms of contour lines. If we want to have salt appears, microbialites in the pre-salt, and these kind of more complex genetic features, we can sketch them this way. Grids are only generated in demand, so everything is surface-based, and only when we want to do some calculations, we create a grid on the fly. The grid is always a nicely structured grid. Played a lot around with the gridding, we test a lot of different gridding techniques to work out how what is most stable, and we found that really what's most stable to create a structured grid and then simply refine the grid to the level where we are happy, where the user is happy to represent the geological heterogeneity at the appropriate scale. Once we have a grid that we're happy with, then we approximate the reservoir dynamics using so-called flow diagnostics that Knut Andreas Lee and Olaf Moyner and their colleagues at SINTEF developed for the last 10 years. So the flow diagnostics are a series of very fast steady state calculations that tend to take seconds to run, and they give us things like information, the reservoir pressure, time of flight, so how long does it take a particle from one injector to travel to a certain distance in the reservoir or from a certain distance in the reservoir to produce a well, reservoir partitioning, which allows us to then look at well allocation factors. So how do the different wells, injector and producer wells, interact? We can also estimate sweep efficiency and define some metrics for dynamic heterogeneity of the reservoir. Because everything is steady state, it's really fast, so it's on the orders of seconds. So we can build models in tens of minutes, and we can get some almost real-time feedback of how the placements of wells interacts with the geological concept, the geological heterogeneity that we are interested in. And before I close, just give you one particular example. So this was a master's project at Imperial College London by a name called Will Jackson. He had about 8 weeks time for his master's project. That was everything from reading the paper, understanding how the software works, understanding the geology of the reservoir he was looking at, to writing his report and writing a paper for peer review that has since been published in a really good journal for peer review. So what Will did is he looked at the Northern Light project, which is the central CO2 storage, envisioned as a central CO2 storage hub for Europe in the North Sea. Formation that is being targeted is shallow marine Johansen formation. A lot of multi-scale geological uncertainties present in that formation. So things, what's the coast, what's the shape of the shoreline, how are things like these small-scale features like calcite, cemented parts in the reservoir that could block, that could reduce the lateral connectivity of the target formation. So a lot of geological heterogeneity at different scale that need to be explored to understand how much CO2 can we store and how fast is the CO2 moving during the injection phase. So Will created an experimental design with 32 reservoir models, sketched these reservoir models really, really quickly in the matter of days in RM, and then used this flow diagnostics engine RM to quantify what the pore volume is available for storage and how long does it would take until how many pore volumes you can inject into the reservoir until you reach breakthrough at a certain distance in the reservoir. Until we also looked at different well locations. As I said, no, this was all done in a few weeks, to the degree that we could publish a paper on this, peer-reviewed paper on this. If you were to try to do this with regular software packages, you would be talking about several months worth of work. So here's one of those models that Will has built, geologically very complex, and that took him again probably 15, 20 minutes to build one of these models. Then he did his sensitivity analysis to screen these different geological scenarios, to look at the amount of pore volumes you can inject and how the different geological uncertainties influence available storage space. And there's actually very little influence on the storage space. There's much more influence of the geological heterogeneities on the rate at which CO2 plume would move away from the well, and a different, depending also different major flow direction where you place the injection well. So he did then a sensitivity analysis on this as well, again, in the matter of probably an afternoon in terms of carrying out the actual calculations. This is now not to say now we're not going to do any further work with, in terms of classical reservoir simulation with the CMGs, Eclipse packages of the world. What we are now is in a position where we can design our full field, full physics, CMJ, etc. reservoir simulation model, and we know already which geological features we need to keep an eye on to really understand how some of the key geological characteristics of the reservoirs that we struggle to quantify, how they could influence the reservoir flow behavior, in this case, the rate at which a CO2 plume spreads, in the more detailed CMG, etc. based full physics simulation. So it's not to replace the commercial simulators, not to replace the WAG and EUR studies that you are doing at LRAP. It's simply to put us all in a position that once we start these complex simulations, we already have a pretty good understanding of how geological heterogeneity, geological uncertainty could influence our flow behaviors before we then spent a lot of time running detailed simulations. So to summarize, what we need to do is we need to ensure that our geological uncertainties are properly considered and integrated with reservoir engineering decisions from day one. With RM, it's one tool that can help us to do this. Geoscience and engineering workflows need to become more agile and honor these three key rules. If you can't draw it, don't model it. You need to get the degree of connectivity and heterogeneity right, and we need to see the geology as the fluid does. So what we really want to do is we need to shift our approach from being precisely wrong to being approximately right first. So don't build big single models that we take really difficult to simulate. We want to build some models that are approximately right first, hone into the key uncertainties, and once we have a handle on the key uncertainties, then proceed building more detailed models that capture then complex WAC relationships, the complex whatever chemical reactions that we may be interested, etc., etc. And with that, thank you very much for your attention, and I hope I just haven't spoken into an empty screen for the last few moments here.
Thank you so
much.
Thank you much. Sebastian, can you hear us?
I can hear you clear, well and fine, loud and clear. Sorry, loud and clear. I can see you as well.
Thank you so much for your fantastic presentation. We have time for some questions here, so I open to the audience. Do you have any questions?
Yes, I have a question.
Luz, please come closer here.
Hi, Professor Sebastian. It's
Hello.
Melina.
Hey,
Hello.
it's good to see you again.
Me too. Well, I have a question. When we are creating a model, what will be the minimum acceptable percentage in the model? By about 10%. I ask this question because when we are building a proxy model, we need to compare the model with full physics simulations, and we use different calculation errors. And normally we can accept this proxy model with 10%, less than 10%. So in this case, what will be the minimum?
So,
percentage?
okay, thank you very much for the question, Luz. So, the acceptable accuracy of the proxy model is, I think that's very much case dependent. So we have done some work on proxy modeling in the past, and where we try to work out, identify the Pareto front in multi-objective optimization, where we spent a lot of effort making sure that the proxy model is really good at where it matters, at the Pareto front, and away from where we're less interested in the results. We were happy with larger errors. So and I'm not the best expert in proxy modeling, but I think for the accuracy of the proxy modeling, rather than looking at just an average accuracy, I would try to get the proxy model right, where the accuracy really well constrained in the area and the parameters which we're really really worried about. How you would combine your proxy model with what I've talked at the moment is, so when we build proxy models, as you know very well, it takes a lot of time to generate the simulations to train the proxy model. And on the one hand, you have the complex physics and the physical relationships, and then you throw in the geological heterogeneity and the geological uncertainties. So you have a number of reservoir models, number of physical parameters for which you need to run hundreds and thousands of simulations to create your proxy model. So what this workflow, this RM idea, what I've presented, what this helps you to do is to think very smartly about how many geological scenarios do we need to begin with, such that we don't need to have 10, maybe we need to train 10 different geological scenarios for our to create our proxy model. Maybe actually we can get away with only 3 different geological scenarios, because these are the key uncertainties that we need to work out. Pre-sort know how the microbialites, the spacing between microbialites or something. That's what we really need to get accurate in the proxy models. We want to have a few models that capture this. And there's a lot of other noise in terms of geological uncertainties that we can ignore. So we really narrow down the number of geological models to train the proxy model at the end of the day, rather than saying, well, we need 10 or 20 or 100 geological models, and we spend even more time and even more computational resources to get your proxy model right.
Mm-hmm. Thank you.
You're welcome.
Thank you, Sebastian. Thank you very much. We are just in time for next presentations of the day. So, Sebastian, thank you once more, and I'll keep in touch with you.
And I hope I see you soon in Brazil again, especially when it's grey and dark outside here in Delft, in Scotland.
Yeah, let's move to make it reality.
Yes.
We are now in phase 2 of the new projects here at the laboratory, and Shell requested us to also study CCS techniques in our project. So we're moving to this area now. So hope we can establish a good collaboration with you at TU Delft as well. I'll keep in touch with you, right?
Yes, please do keep in touch with me. Yeah, there's a lot of interesting CCS work that we're doing, also at really high pressures and temperatures. So if you think about pre-salt CCS type, so we're running similar, not on pre-salt, for other reservoirs. We're doing some experiments at the moment. So very happy to talk to you about this.
Fantastic. Thank you so much, Sebastian.
Thank you. Bye-bye.
See you later. Take care. Bye-bye.
See you. Bye-bye.